All right, so our aim is to, learn differential cryptanalysis on block cipher. So I will give as an example as a differential attack on present. So in order to do all of these, we'll need to learn differential cryptanalysis, but in order to apply differential cryptanalysis, we need to learn present. In order to learn present, we have to learn block cipher. So this is our roadmap, okay? I will explain briefly what a block cipher is. As an example, I will give present block cipher. Then I will explain how differential cryptanalysis works in the following weeks, and then we will apply differential cryptanalysis on present to see if the theory matches practice. All right, so let's start with the basic definition. So historical ciphers mostly operate on letters since they are pen and paper methods. So this is what we did in the frequency analysis, right? So it was a pen and paper method. But then we moved on to, machines like Enigma. Then we moved on to computers, so we have digital data now. When working with digital data, we can represent letters, numbers, symbols, etc. as strings of bits. Okay? Thus, the communicating parties must first agree on an encoding. So this is important. Probably last week I explained when Biham and Shamir first found differential cryptanalysis, they break some Japanese ciphers. So they asked them to send them a few ciphertext and plaintext so that they can capture the key. So at first, due to magnetic detectors, the floppy disks were, malfunctioning. Then they wrote special notes so that they passed through the flight, and Biham and Shamir received the floppy disk. But the problem was that those floppy disks were created on a Japanese language running computer, so they couldn't decode it. So they asked them if they can find a USA computer so that they can create those plaintext and ciphertext. So encoding is important because this way we agree on what we are talking about. Again, in the Enigma, initially British couldn't do it because they couldn't understand how the German is translated there. So Polish mathematicians helped them so that then they could break the Enigma. So this is why we have standards nowadays, so that we don't deal with this kind of stuff. But still, important thing for Turkish people is that Turkish characters, special characters, are not in the ASCII table, but it is in UTF-8. So for this reason, sometimes you receive emails where the Turkish characters looks weird, or sometimes to avoid it, and some people, instead of using Turkish characters, they use some English letter characters that look very similar to, Turkish characters. Like instead of you use E, so that you avoid using UTF-8. But it is 2023 now, so it should be not much of a problem for a lot of people. But still, just check your emails. You will see that deliberately some people don't use Turkish characters when they are sending email. All right, so the ASCII table is somewhat simple. I get it from the web. So there are many, characters. Like in English, you have 26, but you have both capital and, small characters. You have numbers, special characters, and so on. So you have to decide how many bits you need. So if you use 7 bits, then you can represent 128 different characters, like here. But you might need extra characters, so you can use a single byte, which is 8 bits, and represent this code. So some older technology, for instance, email is a very old technology. So in the SMTP protocol, characters are represented as 7 bits. So this kind of encoding sometimes causes problems. Assume that we agreed on an encoding, so everybody understands what we are sending and receiving. So we will be dealing with bits instead in cryptography. So cryptography is a huge area, and new areas are getting added to this area in this science. Most popular ones recently are like homomorphic encryption, post-quantum cryptography, multi-party computation, and so on. So there are many new areas to work on, but more older methods actually solved a lot of our problems. Like we deal with confidentiality, because think about internet. Initially, the security was not a problem because only a few people were planning to communicate, but now it has spread to the whole world. Now you need confidentiality, so you need some fast algorithms so that every internet communication is secure and so on. So we have like block ciphers and stream ciphers here. You can also use public key encryption like Algama and so on, or RSA. But we also have authenticated encryption algorithms which provide both confidentiality and also data authentication. And data authentication can be, obtained by different cryptographic algorithms like hash functions, message authentication codes. This can also be used for entity authentication. You can use zero-knowledge proofs, also digital signatures, which also allows us to have origin non-repudiation. This is important. For instance, think about cryptocurrencies. You digitally sign every transaction, so you use digital signatures there. Actually, for this reason, digital signatures and hash functions, you call them cryptocurrency, not because of these encryption algorithms. Okay, this is a main misconception, because when people think about cryptocurrency, they think that crypto means cryptography, so there must be an encryption involved, but there is no encryption in Bitcoin or in Ethereum or any similar cryptocurrency. So the picture can be, enlarged. I told you that there are homomorphic encryption, multi-party computation, and so on. Post-quantum cryptography is another area that is recently important. So but the good thing is that we have a lot of stuff, and as the people we are interested in cryptanalysis, now we actually check the security of all of these, right? So actually we will be focusing on block ciphers most of the time. We will be dealing with differential cryptanalysis and so on, but in the differential cryptanalysis, you are actually making a small change in the input and trying to observe it at the output. So that idea actually can be applied to many different areas. But also I will show in the next slide, but some of these algorithms use a secret key, for instance, like block ciphers. So as the attacker, your aim most of the time to obtain the secret key. But here, for instance, in the hash functions, you don't have a secret key at all. So the security of hash function depends on some other criteria. Like here, two different inputs can provide the same output. So this is called a collision. So your aim is to create a hash function that is collision resistant. So here, your attacks also will be different. But even though you don't have a secret key here, you can also apply differential cryptanalysis here, because you will give a small input change, make a small input change, and so that two different inputs will try to get the same output. And actually, MD5 collisions are like this. So you are actually performing differential cryptanalysis on the hash function, but your aim is not to get the secret key. Your aim is to obtain a collision. So this is why I'm focusing on the basics. But in the more advanced courses, public key cryptanalysis might be a good focus, because here the security of the algorithms depend on hard problems like factorization problem or discrete logarithm problem. And there are, specific attack types, specific algorithms, and so on. So it is a little bit much different here compared to here. But anyway, we are focusing today here. Yeah, as I mentioned, some algorithms are keyed. So in the symmetric key cryptography or in the asymmetric key cryptography, you have secret keys, but in the hash functions, you don't have. So the security here, not always to obtain the secret key. Same thing applies here. For instance, in the symmetric key encryption algorithms, we have encryption algorithms like block ciphers and stream ciphers, but we also have message authentication codes, which is not an encryption algorithm, but message authentication algorithm, as the name implies. So here, no encryption is involved. So if we go back, as you can see, MAC algorithms are here, not here, right? Because it doesn't provide confidentiality. It is not an encryption algorithm. It solves the data authentication or entity authentication problem. So here, when I try to attack block ciphers or stream ciphers, my aim is to capture the secret key most of the time. But in the message authentication codes, I will try to authenticate a message, although I don't know the secret key. So that means that I'm forging a message. So that is one way of attacking these. Also, if you capture the secret key, then again, you break the system. So there are two different ways to attack this one. Either capturing the secret key or forging a message where you have the authentication. That is the thing. So there are many different algorithms, so attacking them or the security relies on different concepts. So this is what I'm trying to tell you. But in the secret key algorithms, you use the same key material for both encryption and decryption. So block ciphers and stream ciphers like this. In the message authentication code, you use the secret key, not for encryption, but to authenticate the message. So the person who has also the secret key verifies that it is authentic. Okay, so maybe it is not a good idea to write this here, but instead of secret, yeah, secret key algorithm, yes, that is secret key, but not an encryption algorithm, this one. So yeah, the name is correct actually. Okay. Symmetric cryptosystems, block ciphers and stem ciphers are encryption primitives, while the message authentication code is used for data and data origin authentication. We can use a block cipher to build both a stream cipher and a message authentication code, or even a keyless hash function. So I'm saying this because although there are many different areas, you can use one algorithm as the other one. So in order to understand all of these areas, actually you have to learn independently all of them, then rehash it again and then understand what is going on. Because some people are surprised to learn that you can turn a block cipher into a hash function and so. But actually it is not that hard. But anyway. Asymmetric key crypto systems are, somewhat different because there are many different types of algorithms here. Like you have key agreement algorithms, most famous one being the Diffie-Hellman key exchange. Here, two people want to communicate through an insecure channel. So think about internet. So you want to visit Amazon.com and buy something, but since you are going to put your credit card information and so on, it has to be encrypted, right? But you didn't agree on a secret key before because Amazon officials didn't visit you at home and gave you a key, right? Now you are communicating through an insecure channel, but should want to agree, on a secret key. So Diffie-Hellman key exchange actually allows this. So you exchange some messages, and the attacker listens all of these communications and record them. You don't care. But due to the hardness of the discrete logarithm problem, they cannot capture what you agreed on. So after that point on, you can use that secret key, for instance, as your block cipher secret key, and then communicate. And this is actually what happens on the internet most of the time. Okay. But this is just one solution. This is for key agreement algorithms. But we also have encryption algorithms like RSA or AlgoMal. You can use them. Not as fast as block ciphers. And the bandwidth also increases, message size increases in these algorithms, but you can do it. But you can also have digital signature algorithms like elliptic or digital signature algorithm and so on. And again, this is, as I mentioned, most of the time in blockchains and cryptocurrencies, this is what you are using because you are proving that you made the transaction. This way you cannot deny it in the future because you signed it. Okay? But of course, the signatures are everywhere. Even when you download the driver, for instance, NVIDIA driver, it is nowadays larger than 1 GB. But hash of that driver is signed by Microsoft. So when you try to install it on Windows, it realizes that it is signed by Microsoft and says that, okay, this is secure, you can install it. So actually, there are cryptographies everywhere, but most of the time happens in the background, so you don't need to deal with it. For instance, today, most probably, you use all of these algorithms maybe more than 100 times. Your mobile phone did it in the background, but you don't know it. Okay? Yeah, so let's start with some basic definitions. What is a crypto system? I use the crypto system and the word cipher as identical. Okay? Plain text is what you want to protect. Good thing is that it can be, a file on your computer. It can be a WhatsApp message, or it can be my voice and video right here. I'm transmitting through Zoom, and actually it is encrypted via AES. And I will show you again how it is done. A crypto system is a pair of algorithms that convert plain text to ciphertext and back. And ciphertext is the encrypted version of the plain text. And important thing is that ciphertext should appear like a random sequence. This means that you have the plain text, you are using an encryption algorithm and convert it into ciphertext, and this should look like random zeros and ones, so that you transmit it through the insecure channel, like internet. Everybody captures it. We assume that every ciphertext we ever created are stored in some place to be hopefully decrypted back in the future by evil people. But anyway, they record it. But if it looks really like a random sequence, this means that it has no information about the plain text, so that even 200 years later, your very important messages will not be decrypted by secrecy agencies, right? All right, so the person you want to communicate also has the secret key, so they also use it to decrypt your plain text, right? So in the symmetric key crypto systems, we use the same key for encryption and decryption. In the public key, you have one key to encrypt, so you give it to everybody else. They can send you that encrypted message, but only you have the decryption key, private key, so you decrypt it back. So this is the main difference between symmetric key and asymmetric key crypto systems. Yeah, this picture is for the symmetric crypto systems. You use the secret key. So you have to give the secret key in a secure way to the person you want to communicate. If you cannot do it, this is why we have public key cryptography. I mentioned that you can use Diffie-Hellman key exchange to agree on a key, but of course that key is actually something random. But if you really want to use a key that is determined by you, maybe you can send it to that person using RSA or something, right? So there are many methods to, transmit this kind of secret information through insecure channels. All right, so this is the main picture here. So we will use block ciphers as here, okay? So let's focus on block ciphers and the name. Again, in the cryptology course, I explained the history, from there you will understand why we are dividing our plaintext into blocks. But again, we don't have the time for that. Just assume that it is a good thing to do it, okay? So with block ciphers operate on b-bit blocks of data. So your plaintext can be larger than b-bits. So it is divided into b-bit blocks. Each block is encrypted by a secret key K to produce b-bit output. Output blocks form the ciphertext. How do you form them actually depends on mode of operation. Okay. Currently, just assume that we are going to simply encrypt one block and then decrypt it back. So a block cipher and the chosen key is actually a permutation from 2 to the b elements to the 2 to the b elements. This is actually a nice way of looking things, because when you divide your plaintext into b-bit blocks, this means that your input is b-bit and the output is b-bit. So this is actually a mapping. You are mapping every b-bit into some other b-bit. But how you make this mapping actually depends on the block cipher, but also the secret key you chose. And you change the secret key. For instance, all 0 input maybe goes to all 1 output. So once you change the secret key, all 0 input will most probably go to something else. This is why you are using the same algorithm, same input, but different the secret key. So the whole security actually is on the secret key. You publicly announce the algorithm. This is the good thing, and this is what we call the Kirchhoff principle. We say that the algorithm should be secure as long as the key is kept secret. Every other information should be publicly available. This is important because this is where the security lies, because I believe that advanced encryption standard is secure because it is publicly available for more than 20 years, and every cryptographer tried to break it and couldn't break it. So this gives us a confidence, right? But if you secretly design an algorithm and you use it for your military data, some people might think that maybe, it has a weakness, but you couldn't find it. But if it were public, maybe people would find it, right? So this is why we have international standards and everybody is using it. So nowadays, the block size is 64 bits or 128 bits. Rarely we have lightweight ciphers that use 32 bits. But if you shorten the block size, this means that after sending many plaintext or ciphertext, we advise you to update the key so that, because otherwise, 32-bit means that you can at most generate 2 to the 32 different plaintext. So if you send gigabytes of data, actually you exhaust all of the possible plaintext you can send at some point. So this means that the attacker captures every ciphertext possible, and they can use this information to, or maybe in the future they can understand if they see the same ciphertext again, maybe they can understand what the plaintext is, and so on. So you have to update your secret key frequently if your block size is really small. But if it is really small, this means that you are using it on a small device, right, for the IoT or lightweight crypto. But if it is a small device, then updating the key there would be a problem. So this is why we generally suggest, if you need, a small implementation, small cipher, just choose the block size 64 bits, but not smaller than this. But if you are using a regular computer or hardware, you can use a block cipher as 128 bits. This is the case for AES, right? But for the present that we are going to talk about, this is the case. And also we suggest that for personal use, secret key should be around 128 bits. Anything less than this, I don't advise. Why do you live on the edge, right? But if you want military grade security, this means that if you want to secure your data even after 2 years later, then you can, increase this. For instance, Zoom is actually currently using advanced encryption standard with 256-bit secret key in this communication right now. But of course, you have to understand this. This means that if anybody listening this communication when I send my data through the internet, they will not be able to break it because it is using AES-256. But this doesn't mean that nobody can listen to us, because actually Zoom gave us the secret key to use. So a copy of this communication is at Zoom anyway. Actually, this is what happens when when I start talking, I actually press the button, record this on my computer. So I'm taking a local copy. But if I press the, record on the cloud, this would mean that cloud server would actually record and will allow us to download it in the future. So actually, this secret key is also known by the Zoom server so that they can decrypt it back. So you have to understand security in this respect. Using the best algorithm doesn't mean that nobody listens to you, because you didn't choose the secret key by yourself. It was given to you by Zoom, right? So be careful. This is why, Zoom is not allowed in, top officials when they have a meeting and so on. This is why you try to come up with national solutions and so on. All right, so let me explain this permutation stuff. Since you are sending 2 to the B elements to the 2 to the B elements, actually there are many ways of doing this, right? You can map this many elements to this many elements in this many ways, 2 to the B factorial ways. And this is a very huge number, as you can see. Here, 2 is about 2, so 2 to the 2 to the B is a very large number. So there are many different permutations. But when you design a cipher and choose the secret key, actually, at most you can have 2 to the k different mappings, right? So this is a very, very small fraction of this possible permutation set. So in theory, a block cipher is secure if this possible permutations you allowed us to use by the design of your cipher actually corresponds to a nice subgroup of this huge group. By nice, we mean, statistically speaking, it is good. And again, this is not a good explanation, but for instance, think about a mapping from this many elements to this many elements, like this identity mapping. So everything is mapped to itself. 0 is mapped to 0, 1 is mapped to 1, 2 is mapped to 2. So this is also a permutation. But you can think that this actually is not secure in terms of encryption, because everything is mapped to itself, right? So in a block cipher, if I choose a secret key, so that this permutation, it turns into, if it is like the identity mapping, then it would be very bad for us, right? Every ciphertext will be identical to plaintext. Even similarly, even if it is not for every plaintext, there's also some mapping like which simply, inverse the bits. So you put all 0 as the input, the output is all 1, and so on. So this is also a bad mapping for encryption, because just by looking at the outputs and inputs, you can see what the mapping is. So you can decrypt everything else. So there's a huge set of permutations, a really huge, actually virtually infinite. And you are trying to design a block cipher so that it uses good, statistically good permutations. So this is one way of looking at the encryption process, okay? But of course, how you can do it, it is not that simple. For security, for any chosen key, we expect a good block cipher to act like as if it is a randomly selected permutation. This is the idea. Because if you randomly select a permutation, most probably it cannot be the identity permutation, right? Nobody can be that unlucky. Even more, we expect no relation between permutations that are obtained by keys that are related somehow. This is also important. For instance, I chose a key, so I obtained the permutation, right? So I know which plaintext goes to which plaintext. So if I flip 1 bit of the secret key, now this mapping, the new mapping, shouldn't be related to the previous one. This is what this sentence says. This is important because if this is the case, if they are related, and if you don't know the secret key and how it has changed in the second, for instance, think about it like this. For 10 gigabytes of data, we use the secret key. Then I say that, okay, just flip the least significant bit, and let's now continue with this new secret key, okay? So we, again, exchange 10 gigabytes of data. So the attacker has 10 gigabytes of data with the secret key K1, also 10 gigabytes of data encrypted again with the secret key K2. He doesn't know key 1 and key 2, but he knows that their XOR is 0001. This is what we call related keys. So you know the relation, you don't know the secret keys. With this information, sometimes you can capture both key 1 and key 2. Okay, this is what we call the related key attack, cryptanalysis, and so on. And we will also briefly mention why this is important. Okay, so we said that we should design a block cipher so that it looks like a random permutation, but actually there is no very good and academic way of doing it. So we don't know, we cannot prove that this is secure. For instance, advanced encryption standard is secure because nobody hasn't broken it yet. If somebody comes up with a clever idea and breaks it, then we will have another block cipher and use it. That is how things work actually. So this is why we constantly keep cryptanalyzing algorithms to be, and when we discover a new technique, we always apply it to known standards so that if they are vulnerable to this new technique and so on. So this is why, since its publication like 20 years ago for advanced encryption standard, we still having new cryptanalysis results on advanced encryption standard. It still doesn't, cause a problem, but attacks always gets better. So if they reach to a point where the attacks become practical, this would mean that NIST would organize another competition and choose a new standard. That is how things work nowadays. Okay, so Shannon has good ideas for the design. So he is considered as the father of information theory, contributed to the field of cryptanalysis for USA defense during World War II. His landmark paper, Communication Theory of Secrecy Systems, dates back to 1949, introduced the twin ideas of confusion and diffusion for practical cipher design. And the problem is that these are good ideas, but they are abstract ideas, okay? That is the main takeaway from here. So we will try to have a block cipher where it has a confusion and diffusion layer so that, it creates good confusion and diffusion. So confusion, to make the relation between the simple statistics of the ciphertext and the simple description of the key a very complex and then involved one. And the diffusion means that statistical structure of the plaintext which leads to its redundancy is dissipated into long-range statistics in the cryptogram. So again, I will briefly mention what we are trying to talk about, but let me go to the next slide and then give a few thoughts about it. But let me also repeat again, note that the concepts of confusion and diffusion are not measurable. They are absolute concepts, as you can see. Here it says that, complex or good and that kind of stuff, but we don't have a measure for that. So I must say, try to, make these definitions a little bit easier to understand. By confusion, we mean that the ciphertext statistics should depend on the plaintext statistics in a manner too complicated to be exploited by the cryptanalysis. So here we are trying to, hide the relation between the key and the plaintext so that if by looking at the ciphertext, you don't get any information. But here, diffusion idea is a little bit different. Each digit of the plaintext and each digit of the secret key should influence many digits of the ciphertext. So this is actually a nice idea because you can design a cipher so that, for instance, your block size is like 8 bytes. Maybe first byte affects only the first byte of the ciphertext, right? You can design a block cipher like that. But this is not a good idea. This means that there is no diffusion at all because the first byte only affects first byte. This sentence has that a single bit should affect every bit. So actually, statistically speaking, so assume that I have a plain text, I have a secret key, and obtain a ciphertext, okay? So if I flip a single bit of the plain text, I would expect half of the ciphertext bits to be flipped. This is what the expected value actually means that we talked last week, right? Because when you flip a bit, each bit can flip with probability 1/2, right? And if there are b bits, you expect b times 1/2 of them to be changed. This is the expected value in the binomial distribution. Okay, so this is why actually I spent last week about these statistics, because they will come in handy in this kind of topics or to understand how these things work. Here you can think about this kind of stuff as the Bernoulli trials or binomial trials, and also I will also talk about them when we try to measure the success of a cryptanalytic attack, because in order to measure the success probability. You have to statistically explain how the attack works. So we will use binomial distribution there. But it will be for the next time, of course.